All right, so we've been talking about boundary work. Boundary work is the integral of P dV. So if you have an equation for P, then we could integrate it to find the boundary work. It's also the area under the PV curve. So if we can kind of think about what the PV curve looks like, we can calculate the area under the PV curve. Expansion is work out. Compression is work in. Let's see a few different processes and let's figure out, calculate, can we get an equation for the boundary work for these different processes. All right, so let's calculate the boundary work for a constant volume process. Right, let's calculate the boundary work for a constant volume process. Now you might be ahead of me, a few steps ahead of me. What do you think this is going to be? Calculate the boundary work for a constant volume process. So let's say we start at state 1 and we go to state 2. If state 2 is the same volume, and this is volume right here, then I don't know, we might be going straight down to state 2, and boundary work would be the area under that, and there is no area under here. But you probably already knew and could already figure out, I mean, the boundary work is going to be 0 for a constant volume process. Because the boundary's not moving, right? The boundary's not moving, so boundary work is going to be 0. So if you see something like a rigid tank, right? If you are in a rigid tank, if its initial volume is 1.5 cubic meters and its final volume is 1.5 cubic meters, then there is no boundary work. Don't have to calculate it. If something is isometric, then there's no boundary work. Or if it just says it's a constant volume process, then there's no boundary work. Right? I think that was unnecessary, but we just kind of proved, right? No boundary work equals 0 for a constant volume process. Another common process is a constant pressure process, right? A constant pressure process. So what would a constant pressure process look like? Let's say we start at state 1 and we had a constant pressure. We might go over here to state 2 at that same pressure. So if we go from 1 to 2, then the boundary work would be the area under the PV curve. What would this area under this PV curve be? It would be a rectangle, right? It would be a rectangle. Let's calculate this boundary work. Boundary work, what's the area of a rectangle? Base times height. What is the base? V2 minus V1, right? If this is V2, this is V1. What is the height? P. And it's not P1, it's not P2. They're the same P, right? So just say P, right? So here we go. Boundary work for a constant pressure process is the pressure times change in volume. Box that in, write that, put that on your formula sheet, and does that? I think that makes sense. Our units would work out. The boundary work for a constant pressure process is P delta V. Expansion is work out. Compression is work in. If we just do P delta V, then we're probably going to get positive being work out and probably going to get negative for being work in. But remember that I always say that later on when we start putting this into our energy equation, we'll just need to think about, is this work out or work in? Okay? So if something is an isobaric process, remember that isobaric means constant pressure. If it says, hey, constant pressure process, that'll be easiest. If it says constant pressure process, then we can calculate boundary work right here. But sometimes it won't say that. Sometimes it will just be a piston with a top, this weight right here, and this weight can move up and down. So if it is a weighted piston or weighted piston cylinder device, well, if this weight is not changing, then it's going to have the same pressure that it's pushing down on that fluid. So a weighted piston or a weighted piston cylinder device, that would be a constant pressure process. A piston not attached, not attached to a shaft, okay? If this is a piston not attached to a shaft. So if there's a shaft right here, then it might be changing. It might be getting harder to push it up. It might not be constant pressure, but a piston not attached to a shaft is a constant pressure process. Let's kind of write this in words. If the force and the area pushing against the piston does not change, then that would be a constant pressure, right? Because pressure is force over area. If the force is not changing, the area is not changing, then that would be a constant pressure process. And if we have a constant pressure process, the boundary work is P delta V. Remember, expansion is work out, compression is work in. Okay, what about a process? And this actually happens, and it can happen. Seems very specific, but an isothermal compression of an ideal gas. All right, an isothermal compression of an ideal gas. So if we have an ideal gas, oxygen, nitrogen, air, many things we can assume to be ideal, which we won't get into. If right now, if it's obviously a gas, we can assume it's ideal. And if it is compressed in an isothermal way so that the temperature does not change, then let's think about this. This is our ideal gas law, our ideal gas equation, PV equals mRT. If this is a closed system, chapter 4 is closed system, so if it's a closed system, then the mass is constant, right? If it's, as long as it's air, it's not mixing with any other, gases, then this R is constant just because of the fluid that it is, right? R is the gas constant, right? So it's constant the same. All right, and if it is isothermal, then this is constant as well. So if everything on the right-hand side is constant, follow me here, that means PV is constant, right? So if everything on the right-hand side, if the M, R, and T are constant, then PV is constant. So let's kind of rearrange this, and let's say we've got a constant over V. P is a constant over V, so let's call it constant over V. All right, so let's calculate the boundary work for an isothermal compression of an ideal gas where PV is constant. And so this is really just the integral of some constant value over volume integrated with respect to volume. What's the integral of a constant over V dV? Or let's bring this constant out front here. What's the integral of 1 over V? Right, let's bring this constant out front. What's the integral of 1 over V? Natural log of V. Evaluated V2 minus V1. All right, so this is constant times ln of V2 minus ln of V1. Y'all know how we can combine natural logs of things that are subtracted. It's ln of V2 over V1. ln of V2 over V1. So let's circle the wagons here. The boundary work is a constant times ln V2 over V1. Let's write an equation that we can kind of box in. All right, what is this constant though? This constant is PV. So this constant is PV ln of V2 over V1. I'm going to box that in. And so there's an equation that we can use for an isothermal compression of an ideal gas. Isothermal compression of an ideal gas. Now, pressure is not constant and volume is not constant. Should I use P1 in this equation or should I use P2 in this equation? Should I use V1 in this equation or V2 in this equation? Well, you can use P1 and V1 or P2 and V2 because those are equal to each other. Those are constant, right? If they're constant, PV is constant. So you can use either P1 and V1 or P2 and V2. Don't try to use P1 with V2. All right. So, you know, I'm going to write just PV here, but just in my head, I'm going to know, okay, I can use state 1 or state 2. And this V2 over V1, this V2 over V1 is also equal to, let's do a little bit of rearranging here. Let's divide this to that side, that to this side. P1 over P2 equals V2 over V1. So now be careful there, because these subscripts switch. But V2 over V1 is the same as P1 over P2. So maybe I can use P1 over P2. All right. These, we just derived that these were capital V volumes. These are our capital V volumes. So these are volumes. But for a closed system, mass is constant. So if mass is constant, so I could use volumes or specific volumes. Right? I could use volumes or specific volumes because the only difference is we're dividing the top and bottom by mass, and if mass 2 is equal to mass 1, then capital V2 over V1 is the same thing as lowercase v2 over V1 when mass is constant. Okay, so, you know, be careful here because, you know, I would write this on your formula sheet, but there's a lot of things you need to know about that formula. You cannot, especially in this class, you cannot just use formulas blindly when you don't know when you should use them or how you should use them. You should only use that formula when calculating the boundary work for an isothermal compression of an ideal gas. And here you can use P1 V1 or P2 V2. Here you can use V2 over V1 capitals or V2 over V1 lowercases or P1 over P2. Whew. All right? But that equation would give you the boundary work in that process. And so we might calculate it to use in our energy equation later on. Okay? Okay, and how about two more? How about a couple more? All right, let's calculate boundary work for a polytropic process. Now this can happen, very common. And it's not the fact that PV is constant, but PV to some power. And maybe it's a power, maybe it's a N of 0.3, maybe it's an N of 2, or you know, it could be any value. But what if it's not the fact that PV is constant, but PV to some weird power? It's almost like, all right, let's say that we could fit a PV to some power to our graph and to our chart. All right? So, what if PV to some power is constant? Then, and we want to calculate the boundary work, integral P dV. So let's say P is constant over V to the N. P is constant over V to the N. Or maybe let's write it C V to the negative N. Let's do the integral of constant volume to the negative N, integrating it with respect to V. All right, so how do we take the integral? How do we take the integral of anything with respect to that thing? Well, let's take the constant out front right here. And what do? I like to add 1 to the exponent. So now it's, instead of V to the negative N, it's V to the negative N plus 1, divided by the new exponent. The new exponent is negative N plus 1. And we integrate it from 1 to 2, right? So I plug in V2 and I plug in V1. So this is equal to, let's say, the constant is out front still. So I'm going to plug in V2 to the negative N plus 1 minus V1 to the negative N plus 1 divided by negative N plus 1 right there. All right. Now, what is this constant? This constant is PV to the N, right? PV to the N. Now, is this P1 V1 to the N or P2 V2 to the N? Well, either of them, because it stays constant. So I could use either of these right here. So what I'm going to do here now, I'm going to take this constant and multiply it times this first term. And because I've got this V to the 2, I'm going to take this constant as P2. All right, so boundary work. I'm going to take it as P2 V2 to the N, right? That's the constant, times V2 to the negative N plus 1. Okay? Divided by negative N plus 1. All right, now I'm going to take that same constant and multiply it times the second term. But instead of using P2 V2 to the N, I'm going to use P1 V1 to the N times V to the negative N plus 1. When you multiply things together, you can add their coefficients. And when you add N1 and negative N plus 1, what do we get? Really cool here. You get P2 V2, it's almost like those cancel out, to the 1. And you get P1, it's like those add together, we just left with V to the 1. We don't have to write anything raised to the 1 power, divided by negative N plus 1 or 1 minus N. Whew. And there we go. That really simplified down a lot. And we have an equation for the boundary work, but don't use this for any old process. Use this for a polytropic process where PV to the N is constant. That N shows up in our denominator right here. Pretty cool. And so this, let's not use if N is equal to 1, right? If N is equal to 1, then this would be divided by 0. We can't do that. But if N is equal to 1, then this is the previous. This is the previous process. All right. So N is not going to be 1, or else this would be the previous PV to the 1 is equal to constant. Now, this equation does not have to be ideal gas. We did not assume any ideal gases right here. But if it is an ideal gas, then PV of an ideal gas is equal to mRT. So we could do M2R2T2 minus M1R1T1, but this R is a constant. R is the same. M is a constant. M is the same. So we could factor those out and say MR of that material times delta T over 1 minus N. So maybe here's another equation, alternatively, for a polytropic process. So depending on what you're given, we've got another equation that we could use as well for a polytropic process, a process where as it's expanding, it's expanding along a curve such that PV to some power is constant. Okay? So for a polytropic process, in general, you'll be told it's a polytropic process, and you'll be given this in. You'll be given this in so that you can calculate the boundary work right there. Last one, all right, how about the boundary work by a spring piston? So it's not a piston that is just free to go up and down. It's a piston that has a spring attached to it. So you can imagine the further and further you go up, the harder and harder it gets to push on this. So let's say it moves a distance x. Whoa, sorry here. Okay. Let's say it moves a distance x right here. And the force in the spring is K delta X. So you can imagine the force in the spring will increase linearly with X. Force in the spring will increase linearly with X. If the cross-sectional area is constant, which is a good assumption, because if it wasn't constant, then this top would not fit snugly, right, in this piston cylinder device. If the cross-sectional area is constant, then the pressure, right, if the force and the area, force is increasing linearly and area is constant, then the pressure will increase linearly. Will increase linearly with x. Will increase linearly with x. And if the cross-sectional area is constant, then the pressure, this is what we're getting to, will increase linearly with volume. Because the difference between x and volume of a cylinder is just cross-sectional area, right? Volume is cross-sectional area times x, and if cross-sectional area is constant, then v kind of behaves similarly to x. P will increase linearly with x. What would that look like on our PV diagram? Let's start at state 1. It would go linearly, let's say that's a straight line, to state 2. So what is the boundary work? The boundary work would be the area under this curve. How about we break it up into this area plus this area, right? That area plus this area. So this area would be the boundary work done to expand if there was no spring. All right? So if there was no spring, then, right, this would just be this P delta V. All right, now that there's a spring, we still have this area under the curve right here. We still have the P delta V, but now we also have the boundary work due to the spring compressing. Boundary work due to the spring compressing. So the total boundary work, if we have a piston cylinder device that is attached to a spring, the spring is pressing against it, and it's pressing harder and harder the more we compress it up, the more we compress the spring up. All right, so what would the area under this curve be? It would be the area P1 V2 minus V1. That's the boundary work. That's this rectangle right here. The boundary work just because it's expanding. Plus, what's the area of a triangle? 1/2 base times height. This height would be P2 minus P1. All right, so we could box that in, right? We could box that in. Or we could do a little bit of math, factor this out. Factor that out. V2 minus V1 or delta V would be P plus, let's see, P1 and P2 divided by 2. All right, this would come out to be, I'm not seeing it here, but P2 plus P1 over 2 times V2 minus V1. This is kind of the, what if we take this as a trapezoid and take that area, right, this area of this rectangle would be the same as the area that we had just done, and that area right there would be the average of P2 and P1 would be that height times the base V2 minus V1. We could figure it out mathematically, right, why that would be the case. All right, so anyway, there we go. I would just write that equation, memorize that equation. But again, that we can't use any time for any process. That's only for the expansion of a piston cylinder that has a spring, right? Expansion of a piston cylinder that has a spring attached to it. And this change in pressure is due to the spring. P2 minus P1 is due to the spring, right? It's a force over area, right? P2 over P1 is due to the spring. It's the force over area of the spring. It's the K delta X divided by area of the spring. So if you're told the spring constant, if you know the change, the delta X that it moves, how can we find delta X? We might know delta X by knowing the delta V. If we know the delta V, we know the cross-sectional area, we can find the delta X. Delta X times K would be the force divided by the area. That would be the P2 minus P1, the change in those P's. Okay, but anyway, here we go. Boundary work for a piston cylinder device that has a spring pushing down on it. Average of P1 and P2 times delta V. Okay, so right now we're not worried about what we're going to do with this boundary work. We're going to use this later. But right now, we're only concerned with calculating boundary work for different processes. So let's put these into practice. Let's put these equations into practice for different processes. All right?